Hello and welcome to week 6 of IT in the Forge. We're going to continue our dive into how computers compute by looking closer at the CPU. But before we talk more about what a CPU does, let's actually talk about what it works with, and that's binary. Now the language of binary is what we call a base 2 numbering system. And to explain what that means, let's look at a numbering system that we're already familiar with, the base 10 numbering system, aka the decimal system, deci meaning 10. The decimal system has 10 unique digits, 0 through 9. When counting up in the decimal system, when you run out of digits, all you do is add a place value and reset back to 0. For example, after 9 comes 10, after 99 comes 100, after 999 comes 1000, etc., etc., etc. Furthermore, a large number can simply be thought of as adding all these place values together. For example, the number 736 can be thought of as 7 hundreds plus 3 tens and 6 ones, 736. Things work the exact same way in binary, except we only have 2 digits to worry about. Want to take a wild guess what those are? 1 and 0. We can start counting at 0, then 1, but we've run out of digits. So now we need to add another place value, except instead of this being the tens place, it's going to be the twos place. And then we reset the lesser place value to 0. So a 2 in binary actually looks like this. 1, 0. A 1 in the twos place and a 0 in the ones place. Essentially we have 1, 2 and 0 ones here. You add those together, you get 2. A 3 would be represented by 1, 1. 1 in the twos place, 1 in the ones place. So you have 2 plus 1 is 3. But here we go again. We've run out of unique digits. So what do we got to do? We got to add another place value. Next up is the fours place. 4 would be 1, 0, 0. 1 in the fours place, a 0 in the twos place, and a 0 in the ones place. 5 would be 1, 0, 1. 6 would be 1, 1, 0. 7, 1, 1, 1. Here we go again. Next is the eights place, 1, 0, 0, 0. We can generally call each place value here a bit, which is short for binary digit. A bit is always just a single 1 or a 0. Now you get 8 bits together and you have a byte. Arr. In a byte, the place value furthest to the left is the 128th place. And if you have every single bit in a byte on, then you have a value of 255. Now it's really great that we can represent numbers with binary, but where things really get interesting is when you realize that you can represent just about anything with numbers. Letters, symbols, colors, sounds, just about anything can be represented with a numerical value. And one of the earliest examples of this was what was called the ASCII index. ASCII is short for American Standard Code for Information Exchange. And what the ASCII index did was map numerical values to various instructions and symbols, including decimal numbers and the English alphabet, both lowercase and uppercase. For example, an uppercase A is assigned the number 65 in the ASCII index. Represented in a byte of binary, that's 01000001. And uppercase B is the number 66, or 01000010. You may have seen colors on a computer represented by RGB values before. RGB is short for red, green, blue. By adding different values of red, green, and blue light, we have access to a broad spectrum of colors. For example, RGB 255, 130, 200 is a bright pink color. And here's those numbers broken down into binary. With a single byte of information, only 256 possibilities exist. That's all zeros all the way to all ones. As the use of computers became more global and the need to represent other languages so that nations could collaborate with each other grew, the limitations of the ASCII index were eventually supplanted by something called Unicode. Now the ASCII index is only an 8-bit code, which means only 256 possible numbers exist. Now Unicode is a 16-bit code, which means over 1 million possible numbers exist, which is more than plenty for all the languages in the world, including emojis. Now, while storing and representing numbers and different things in binary is useful, the real goal of computers is computation, or rather manipulating numbers in a structured and meaningful way. And this manipulation is made possible by the Central Processing Unit, or the CPU. Now, the main function of the CPU is to execute, or run, programs. And programs are made up of a series of individual operations called instructions. Now, instructions can be stored and addressed in memory, just like data. Remember when we talked about that in RAM? The grid and all that good stuff? Now, there's a process by which a CPU retrieves instructions, carries out those instructions, and then sends out the results. But first, let's look at the 4 main parts of a CPU that make up what we call its microarchitecture. Those 4 parts are the control unit, temporary registers, the arithmetic logic unit, or the ALU, and the clock. Think of a person sitting in a small room. In front of this person is a desk with some trays for papers, a calculator, a phone, and a metronome. This person receives a call to retrieve some data. The person then dials a specific number to get the data they need. Data arrives in the room and is stored in the available trays. The person must then look over the data to understand what must be done with it. Once this is known, the person will perform the necessary calculations to get a result. Lastly, the person sends the results out to an address specified in the instructions. In this example, the person is the control unit, the paper trays are the temporary registers, the calculator is the ALU, or the arithmetic logic unit, and the metronome is the clock. Now, this whole process is broken down into 3 phases. The first phase of this process, when the control unit retrieves the needed data from the memory, is called the fetch phase. This is followed, secondly, by the decode phase, in which the control unit separates the data into temporary registers and identifies the instructions for that data. The third and last phase is the execute phase, in which the ALU is used to perform any necessary calculations, and the rest of the instructions are carried out. The ALU is essentially the mathematical brain of the CPU. It performs arithmetic and logical operations by using logic gates. Remember those? Values are received and instructions for what operations to run on those values. The one thing we haven't mentioned yet here is the metronome, or the clock. Each of the actions above occurs in sequence at the tempo of the clock. While our example here is slowed way down to make sense, this entire processing cycle, fetch, decode, execute, occurs at every click of the clock. The clock speed of modern processors is measured in gigahertz, meaning this cycle is completed billions of times per second. Per second! The combination of these 4 parts is what we commonly refer to as the core. More cores equals more data processed per click of the clock, and modern processors often have multiple cores. There are 2 primary manufacturers of CPUs today, that's AMD and Intel. It is very important that you research the make and the model of a CPU before making a purchasing decision. Certain motherboards only work with certain models and makes of CPU, and there are many different models of a CPU that come from the exact same microarchitecture. Now, as we discussed when we were talking about motherboards, CPUs are made to fit some very specific sockets. The 2 most mainstream sockets are the LGA 1151 for Intel and the AM4 for AMD. The last analogy we really need to understand is how to keep that person cool with all that work they're doing. If that person crunching all that data didn't have any kind of air conditioning, then they would burn out pretty quick. In accordance with the laws of physics, the amount of bit crunching that a CPU does can generate a lot of heat. Remember, what's really going on there are just tons of little electrical switches flipping on and off really fast. Too much heat can permanently damage a CPU, or at least severely affect its ability to perform the job that it needs to. Proper cooling is achieved by using simple fans or fancy, more efficient liquid cooling systems. These devices are attached directly to a CPU with a certain amount of what's called thermal paste in between the 2. Thermal paste provides a more uniform contact between the fan and the CPU so that heat can transfer more efficiently. Wow, that's a lot! But now you have a really high level knowledge of how computers do exactly what they do. If you plan on pursuing a degree in computer science, then you'll dive even deeper to a lot of these topics and the details of this process. And as always, even if your aim isn't higher education, there are tons of free resources available out there to learn more and more about these things. And I encourage you to seek those out. Thanks for hanging on today, and we'll see you next time in the Forge.